right, everybody, I think I'm going to go ahead and get started because it's 10 o'clock. Welcome to Tuesday. I hope that you are having a good week so far and hanging in there, hopefully getting into the rhythm of the semester by now. I got a couple announcements and then we'll dive right into the math today. This is the last week for you to stop by for a 5-minute intro. If you have not done that yet, either in Zoom or in person, this is the last week you can do it and actually get credit for it, in the sense that I'm going to offer extra credit on each of our midterms for people who've stopped by to say hello. I think most of you have done it, but there's a few people here or there that have not had a chance to stop by yet. No worries, just try and do it this week. I promise it only takes 5 minutes, and you just have to introduce yourself, and I'll let you know anything that, I'll let you know where my office is, for example, if you stop by. So please try and do that. That would be super, super swell. Otherwise, this week is a pretty normal week. My usual Tuesday, Friday homework is going to happen this week. There's an assignment due tonight. It's actually very short. And I'm going to do those 2 problems from the assignment in just a few minutes as well. So it shouldn't be stressing anybody out, I hope. There was a video that I asked you to watch. It actually was not my video, but it's a 15-minute example of the Gauss-Jordan method. So that'll take just a few minutes. And then beyond that, there's just a small number of problems to work on from this current section that we're working on. So anyway, so that's tonight's homework. And then there will be an assignment due on Friday as well. And I can give you a heads up about that. That's also going to be a relatively straightforward assignment. It's mostly very computational. It goes really, really quick. So this week's homeworks are not too crazy, in my opinion. Next week, we will not have a normal week because next week on Thursday is our first midterm. So I'm going to talk about that after our break today. So stay tuned. I will give you a heads up about what that midterm is going to cover and how I think you should study for it and what to expect. Okay, so we'll do that in a little while, but I'd like to get right into the math today at the beginning, if I can. And then I will sprinkle in those homework questions as part of my little lecture here. If anybody wants to add anything else to that list, feel free to do so. Remember, guys, there are some true-false items on a lot of these assignments. You should do those. Those are kind of quick little concept testers. On the true-false items, you need to give me a quick little 1 or 2 line reason why you said it was true or why you said it was false. And you can put those on the sideboard too if you're thinking it would be helpful to look at. So just keep that in mind. As we go through the semester, you're going to see more and more of those as well. So anybody have any questions before we jump in today? Yeah, go ahead, Brian.
Do you get partial credit for midterm problems?
Yes. Oh, for sure. For sure. Yeah, absolutely. There will always be partial credit as we go along. Okay. Without further ado, I'd like to pick up where we left off last Thursday. We were talking about this idea of an invertible matrix. I just want to remind you again what it means. For a matrix to be invertible, first of all, it has to be an n by n size. So it has to be a square matrix with the same number of rows and columns. And a matrix is invertible if you can find another matrix, which we ultimately call A inverse. So you have to be able to find another matrix that when you multiply it with the original matrix, it cancels out to the identity matrix. So this I sub n is one of the most important matrices in linear algebra. I sub n is just the matrix that behaves like the number 1 under multiplication. So if you take the identity matrix times anything else, you just get that same other matrix back again. Anyway, so this is the condition. A times A inverse equals the identity. Right. In the case of a 2 by 2 matrix, so if n is 2, it's real easy to not only test for invertibility, but also to find the inverse. So the inverse of a 2 by 2 matrix, I should have been more clear here, guys. The matrix A on this 2 by 2 case is just set up like this. So the A and the B are in the first row, C and D are in the second row. In that case, the inverse of A is given by this matrix here, where the letters are a little bit scrambled up. Notice that the the A and the D swap places, right? And the B and the C pick up sign changes, minus signs, right? So, and then out in front, you have 1 over AD minus BC. Obviously, if AD minus BC was equal to 0, then this just wouldn't make any sense. And in that case, you don't even have an inverse, right? That would be a matrix that's not invertible. So for a 2 by 2 matrix, the story on inverses is really simple. It's just what's in this box. The formula is right here, and it'll exist as long as you're not dividing by 0 out in front. Okay? So far, so good? Just interrupt me if you've got any questions about this. Is just a recap, just reviewing what we did last week, kind of get it back in our heads again. But feel free to slow me down with a question if you'd like to.
So for the inverse of A, it's always going to be that where the diagonals like D and A, they're going to reverse themselves, and then the opposite is going to be the signs.
Yeah, for a 2 by 2, when n is equal to 2, this is the formula. And we even checked it last Thursday. Like we took this formula, we multiplied it by the original A again, and just checked that we got back to the identity matrix. So you can always confirm. If somebody ever claims that the inverse of one thing is another, you can always check that by just multiplying the two things together to see if you actually get the identity matrix. So there's always a way to kind of confirm that these answers are correct.
Is that the same format if it was a 3 by 3?
Oh yeah, any side. Well, for a 3 by 3, I don't have a form for the inverse, but this is still true.
Okay.
Absolutely true. Yeah.
Is it okay to use Gauss-Jordan for a 2 by 2? Yes.
Yeah, you can even use the Gauss-Jordan method for a 2 by 2 matrix. However, it is almost certainly going to be longer than just knowing this formula. I would recommend for a 2 by 2 that you just use the formula, but it would not be wrong to use the Gauss-Jordan method. Yeah. Other questions so far? Oscar.
As far as like the midterm goes, you said that we would have to memorize most of the formulas, right?
Okay, I'm going to talk about the midterm after the break today. Okay, so we'll come back to that, and I'll pull it up on the screen, and we'll get into the nitty gritty about that. What I've got here is, so remember that when the matrix is 3 by 3 or larger, so if n is at least 3, guys, then there is no standalone formula for A inverse. In that case, instead, what we have is a method. It's called the Gauss-Jordan method that allows us to derive A inverse through, as you can see, a process involving EROs. So I derived this, or I explained the theory behind it last Thursday. You set up your matrix here as an n by n matrix on the left side of this bar. And then on the right side of the bar, you put your identity matrix. And what you're going to do is you're just going to proceed to do EROs in an effort to get the identity matrix to show up on the left side of the bar. And if you're able to do that, and I say if because you can't always do it, but if you're able to get the identity matrix on the left side, then your A inverse will be immediately appearing on the right side. That's how the process works. It's very computational, but it's not very heavy on conceptual work when you're actually in the midst of the process.
And if you can't get it to be on the left side, then you know that it's not an inverse, right?
Correct. That's right. So if you are unable to get the identity matrix on the left side, then that's just your red flag that this matrix does not have an inverse. That's right. So anyway, yeah.
This last question, like if you're on during the exam and you're trying to solve for it to find if it is an inverse, and you're just like stuck, you're just questioning yourself whether it does or doesn't. Like, how does that work?
I'm going to give you some more tools. We're not there yet. There's other ways to test whether a matrix is invertible besides just fumbling through these EROs. So I'm going to come back to that. That's a really good point. So as I mentioned on the homework for tonight, I asked you guys to watch a little 15-minute video online about somebody actually, it was a 3 by 3 matrix, just doing the Gauss-Jordan method. I hope that you've had a chance to watch that. I'm going to do one more warm-up example to practice it one more time with you. So let's just try this example that I've put on the board here. I've got a nice little 3x3 matrix, which is a good size to work with. And I would like to find A inverse. I should have added, if possible. We don't really know just glancing at it if it even has an inverse. But let's just try it, okay? So I'm going to come over here and solve this warm-up problem by doing the Gauss-Jordan method. So the first step is to set up your block of matrices with the A matrix on the left side. So I'm just going to recopy the given matrix on the left. And then on the right side, I'm going to put the identity matrix, which for a 3x3 matrix is going to look like this, with the ones going down the main diagonal on the right side. Okay, so this is the starting point, and we're going to just start doing some EROs. And Raphael makes a really good point. We don't really know right now if it's even going to be successful, right? We're kind of just going to take a stab at it and see if we can get the identity matrix on the left side. Now, if you take a look, my upper left corner here is already a 1. That's super helpful. So based on this pivot already being in place, would anybody like to suggest a good ERO to start with? Go ahead.
Josh, add the third row, like the first row.
1 and 3.
First row to the third row with what multiple?
-2.
With -2. Exactly. I'm going to take -2 times the first row, and I'm going to add that to the third row. When I do that, the first row does not change at all. Obviously, we're not even talking about the second row, so that does not change at all. But -2 times the first row being added to the third row will get me a 0 right there, which is really the key thing I want to achieve. And then -2 times 0 gets added to 3 and becomes 3. -2 times 1 gets added to 6 and becomes a 4. -2 times 1 gets added to 0 and becomes a -2. Here we have 0 times -2 added to 0, which is just 0. And 0 times -2 added to 1 is just 1. And if I look at my progress here, I see now that I do have a good pivot in the second row as well. Okay, so far so good. Can I get a suggestion for the next ERO that would be a good idea? Brandon? A2, 3 of -3. Beautiful. So I'm just looking at these two numbers. And if I take -3 times the second row and add it to the third row, I'll get a 0 below that pivot. And that's always the key. So the first row does not change. Just recopy it. The second row does not change. I'll just recopy it. It's only the third row that is actually going to feel the effect of this ERO. So -3 times the second row added to the third row will give me a 0 and a 0. And then let's see, -3 times 1 added to 4 is a 1. -3 times 0 added to -2 is just still -2. -3 times 1 added to 0 is -3. And -3 times 0 added to 1 is 1. And I've now got on the left side a row echelon form. So I can see that this would have been good enough if I just said, what's the REF of A? It would just be, this matrix would be a good answer. But of course, I'm not done. When I do the Gauss-Jordan method, I actually have to keep going to try to actually get the identity matrix to show up on the left side. Looks to me like the first two columns are pretty good. The only real issue here is that in the third column, the ones that I see need to become zeros. Is there a way to achieve that?
It'd be A32 multiplied by -1.
A32 of -1. So what Raphael's saying is, let's take the negative of the third row and add it back to the second row, because he wants to turn this 1 into a 0. And is there another ERO that we could do at the same time, Brandon? A31 of also -1, exactly. So I can take the negative of the third row and add it to both of the first two rows. So let's just do that. By the way, when I do that, the third row does not change at all. So I'll just recopy the third row since that's not being affected. But the negative of the third row added to the second row, the negative of the third row added to the second row is going to give me a second row of 2, 4, and 1. Doing a little mental math in my head. At least it's not a Monday morning. It's a Tuesday morning, so we can handle this. And then the negative of the third row added to the first row. Am I doing okay?
Isn't that 2, 4 negative?
Oh, you are absolutely right. Maybe it is. Has to be a -1. Sometimes I like to make little mistakes on purpose just to see if anybody's paying attention. So, yeah, so that should have been a -1. All right, now let's also take the negative of the third row and add it to the top row. If I do that, I'll get 1 and 0 and 0. And then negative of -2 added to 1 is 3. Negative of -3 added to 0 is 3. And negative of 1 added to 0 is -1. And if I have done that correctly, I'm just going to check my notes. That is your A inverse. That is your A inverse matrix. Does that look okay? So that's the Gauss-Jordan method. Let me actually follow up with a little follow-up question. I'd like to see what you think here. What if I asked you to solve x plus z equals 7, y plus z equals -1, and 2x plus 3y plus 6z equals 2. So a little follow-up problem that this should be good timing for. Now, one way to solve this problem is to just simply, so I'll just say method number 1. One way to solve any linear system of equations, as we learned last week, one approach that we always have is to just write out the augmented matrix and do your EROs and then apply what's called Gaussian elimination to it. That's where you solve by back substitution once you get it into row echelon form. So that is, of course, one way to do it. However, it's not the best way to do it right now based on what we've already done. Does anybody notice anything about this system that's kind of relevant based on where we've come from? It looks to me like the coefficient matrix here. The coefficient matrix, so the coefficient matrix would be 1, 0, 1. 0, 1, 1, and 2, 3, 6. It's exactly this matrix that we just played with, right? So this system, I'm going to call this method number 2, and this is going to be the one that I want to try to take advantage of right now. Method number 2 is to just simply treat this system as an equation. A times x equals b, okay? Where the A is, the same matrix as above. So I'll just write it down here, 1, 0, 1, 0, 1, 1, 2, 3, 6. And then the B vector, the B vector is just on the right-hand side. That's just going to be these numbers here that are up here on the right-hand side. So 7, -1, and 2. So you can view the linear system in this form instead. Now, what's nice about doing method 2 here, guys, what's nice about method 2 is that we already know that A has an inverse. And in fact, we already found it right here. And so what I can do is I can solve for x by using the A inverse and multiplying by b. Do you guys remember this? The idea is we can essentially, it's like dividing by a is more or less what we're doing here. So that's exactly what we want to do. And in this case, guys, we already have the A inverse matrix. It's 3, 3, -1, and 2, 4, -1, and -2, -3, 1. And I'm just going to multiply that by the B vector. I'm going to multiply that by the B vector that we wrote down. So this is just going to be a little matrix multiplication now that I have to calculate it. Make sense?
Could you recap? Just because
This one?
I was dragging, I'm going from like
I'm
method
just
two.
solving for x by moving the A inverse to the other side of the equation.
Okay.
And I'm going to take the A inverse, which we actually already found in the first regular part of the problem. I'm just going to multiply it by this. This is the B vector here.
Okay.
Yeah. Kim?
So in the use the second method, we have to be verify that there's a inverse.
To use method 2, he's making a really good point. To be able to use method 2, I have to have an A inverse that I can write down. Okay, so method 2 would not work, right, in every problem. So that's why method 1 is so important, because if the matrix isn't a square size, or even if it is, if the matrix is not invertible, you will have to use method 1, right? Method 2 is only going to work when A is invertible. And in this case, we can now just multiply this out using our usual dot product matrix multiplication process, right? So let's just do it here, guys. The first entry is going to be 21 minus 3 minus 2, right? 21 minus 3 minus 2, which is actually 16. And then on the second row, I have 14 minus 4 minus 2. Well, 14 minus 4 minus 2 would be 8. And then on the last row, I have negative 14 plus 3 plus 2, which adds up to negative 9. It adds up to negative 9. And so this becomes your Z value. So the bottom entry is the Z value, the middle entry is the Y value, and the top entry is the X value. If we wanted, we could write this as 16, 8, negative 9. Okay? Actually, let's just review something again from last week. If I have a linear system of equations like this one, what are the possibilities for how many solutions it might potentially have? Infinitely many, that's one. Well, what was another possibility?
One solution.
Exactly one solution. And what was another possibility?
No solution.
No solutions, right? So 0 or 1 or infinitely many. But do you notice that when the matrix is invertible here, the coefficient matrix, when the A is invertible in your system, it's turning out that in that case, there is always going to be one solution for X, because it's exactly this, A inverse times B. So of your 3-case scenario, right? No solutions, one solution, or infinitely many solutions. These are the 3 possible outcomes of, the solving the linear system. It turns out that when A is invertible, it's got to be this one. And we even know what the one solution is. It's A inverse times B. Now, I see some of you trying to maybe write all of that down that I just spoke out loud. No worries. I'm actually going to write it down in your notes in a few minutes when we get to the spot where I'm going to kind of do a big summary. So I'm not going to write it down at this moment, but it's a good moment to make the observation. When your matrix is invertible, you will always get one solution, right? No more and no less. Always one solution. And this example kind of shows that. So far, so good? Okay, so the problem with this section that I have is that we kind of get distracted by the Gauss-Jordan method, which is very computational, very ERO driven, and you get very kind of lost in the calculations, and it can be very easy to forget what invertible really means and what the power of that really is. But I would actually like to take a minute. I'm going to so far I've been doing very computational. I'm going to take a few minutes and kind of drift over into the theory side of this And a great way for me to do that is to present a theorem for you here that will allow us to sort of appreciate this theory a little bit. So here's the theorem. I'd like to write this down. If A and B are n by n matrices, I'm sorry, n by n, I'm sorry, I miswrote that. It should be n by n invertible matrices. If A and B are n by n invertible matrices, then there's actually two things that I'm going to say here. The first one is that if you multiply them together, so if you take two n by n matrices and you multiply them together, you'll get another n by n matrix, A times B, and this is still invertible. And I can even give you the formula for the inverse of this matrix. So if I want to know, well, what would be the inverse of A times B? It turns out that the answer is you take the individual inverses of A and B, which you are assuming exist in the first place, and you multiply them together in the opposite order. I'm going to explain this, okay? So everybody will see, hopefully in a minute, we'll justify that. In fact, leave yourself just an inch or two of space. I'm going to justify that in that white space in just a minute. But before I write down the justification, I want to write down the second statement as well. So not only when you multiply two invertible matrices, you still get another invertible matrix, but another fact is that if you were to transpose a matrix, so if you took the A and you swapped its rows and columns, that does not change the fact that the matrix is still invertible. So A transpose is invertible, and then you, of course, will want to know, if I'm telling you it's invertible, the question will be, well, what is its inverse? And again, the answer is very nice. The inverse of A transpose turns out that all you have to do is find the inverse of the original matrix and then transpose that. Okay, so it actually works like that. It actually works like that.
Isn't that a property?
Yep, we're going to prove it right now. This is these are two properties about inverses, and it's kind of theoretical, so I wanted to have a chance to practice the theory, and this theorem gives us a great chance to learn something new and practice the theory at the same time. Okay, let's try it, and this is what we're going to need on those two homework problems that are on the board over there, by the way. This same exact approach. So let's do this proof, and then once we've done this theorem, I'll do those two homework problems also. All right. How do I show that the inverse of one matrix is another? Right. So if I want to confirm that two things are inverses of each other, right? I was reviewing this earlier. It just amounts to multiplying the two things together and making sure that you get I. Okay, so I'd like to do that here. And guys, it's only one line. It only takes me one line to do this. I'm going to take my matrix. Now on the left side, it's just A times B. That's my matrix. And I'm going to multiply that by what its inverse is supposed to be, or according to this statement, what it's supposed to be. So what they've told us is that the inverse of AB is B inverse times A inverse. So I'm doing this very abstractly. And I'm simply saying, okay, how do I confirm that? I confirm that by multiplying the two things together and hopefully getting I. Now remember that we're not allowed to switch the order of anything. But I can tell you that the parentheses, we have properties of matrix multiplication, the parentheses don't matter. And in fact, I can regroup things however I want. And what I'm going to do right now, guys, is group that B inverse that's in the middle. I'm going to kind of group that together. What do we know already that B times B inverse will be equal to? The identity, right? It's equal to the identity. So isn't this just A times the identity times times A inverse? Right? So that identity matrix just finds its way into the middle there. Do I need to write down the identity matrix? Really?
Not really.
Not really. It's like multiplying by 1. So, if you had 7 times 1 times 1 7, you'd probably stop writing the 1 down. Well, I'm going to do the same thing here. I'm just going to stop writing the I inverse, the I sub n down. And what I'm left with is just A times A inverse, which by the way is equal to what? The identity again, right? So it actually confirms it. It actually confirms it if I multiply AB times what its inverse is supposed to be according to the statement, we get I. Notice the way this works, guys. You see the inverse here on the left side of the statement? We did not write that down here. We just wrote only the AB because we're claiming that it is the inverse of AB is this other thing. So I have to check with AB what I could multiply it by to get I. So that's why I'm not writing the inverse, this exponent, anywhere on this line. You don't see the AB in parentheses with an inverse on it. Okay?
When you write the A times B, the first one where it's parentheses A times B, the inverse,
Mhm.
that's the same thing as B inverse of A. The left side,
This thing here is what you're talking about?
yeah, that is the same thing as the right side.
Yeah.
Okay.
That's what we're proving.
Okay.
Yeah, we're justifying that right here. So this is the justification. It's a one-liner to justify that. Okay. By the way, does anybody remember another situation where we had to switch the order like this with two matrices that are multiplied together? Do you remember not with inverses, but with something else that we did a while back? It was by a while back, I mean like a week ago, where we wanted to multiply two things together, but then when we did some property, we had to switch the order.
believe
Arnold?
this was transposing AB.
That's it. That's really good, guys. So just I'll use different letters here so we don't get it confused with our theorem right now. But you might remember that if you transpose a product of two matrices, we also had to swap the order of the two matrices. So I'm going to use X and Y just to not confuse it with the letters that we're using in our theorem. But it's kind of nice to know that this transpose behaves the same way with multiplication as inverses do, which is that you have to switch the order. If you want to break it down into the individual transposes, that's fine, but you have to switch the order of it. Same thing for inverses here. Okay. Let's try this second part, guys. And again, I'm only going to need one line. This one's actually going to be even shorter, I think. I would like to show here that the inverse of A transpose is equal to this thing on the right side. So to do that, I'm going to follow the same approach. I'm going to just take the A transpose and I'm going to multiply by what it says the inverse should be, which is on the other side of the equal sign. So I'm taking this A transpose right here. I'm going to multiply by what its inverse should be. And again, what am I hoping that this is equal to?
The identity matrix.
The identity matrix, right? That's how we will know that we've done it correctly, is that this should be equal to the identity matrix. Okay, let's check it. Let's check it. So how can we proceed? So does anybody have a suggestion for what I could do on this step right here? Use the thing I just wrote down, right? The transpose of one thing times the transpose of another thing can be combined into a single transpose as long as I switch the order. That's exactly what I'm going to do. I'm going to switch the order, which means I'm going to put the A inverse first, and then I'm going to put the A second. But otherwise, it's literally just using, maybe I'll just put a little star here next to this property. And then by this equal sign, I'll put a star. That should remind us where that's coming from. So we're just switching the order of the two matrices. Now, what is A inverse times A?
Identity matrix.
Identity matrix, I've still got a transpose on it, but that's the identity matrix inside those parentheses. And what is the transpose of, well, let's just write down. Let's just remember here, guys, the identity matrix. Remember this one? This is the one that has the ones down the main diagonal and zeros everywhere else. What happens to this matrix if you transpose it? You switch the rows and columns.
It would stay the same.
It stays exactly the same, okay? It stays exactly the same. Transposing the identity matrix actually does nothing. So you might as well not even bother with it, right? It is just the same as the identity matrix. And again, I've got my check mark here because at the end of this line, I have derived the identity matrix. Good enough? So these are nice properties anyway, but they are really nice for us to practice the definition of invertible matrices. Okay, with that in mind, I would like to tackle the two problems that are up here from tonight's homework. And I'm just going to do them for you. And you're going to see just how fast they are. I'm actually going to do 35 first, and then I'll go backwards and do 34. Okay, so I'll do 35 and 34 from the homework that's due tonight. This is the perfect timing for this. So let's do it. Come over here and 35 on section 2.6. Number 35, it just says, assume that there's a matrix A whose 12th power is equal to 0. In the book, it writes it as 0. I'm going to put a little sub n on it to really emphasize that we do have a matrix here. So assume that, and then it's asking us to prove that the identity matrix minus A cubed is invertible with identity minus A cubed quantity inverse equals identity plus A cubed plus A to the 6th plus A to the 9th. So this is one of your homework problems for tonight's assignment. And I want to just solve it out with you here. And as you can see, this is all the more room I'm going to need in order to do it. It's very short. Kind of goes along the same lines as the ones we were just doing, right? I'm showing that the inverse of one thing is equal to another thing, right? And how do I do that? Well, I just multiply the two things together and I try to get the identity matrix out of that. So let's try that here, guys. On the left side, I have identity matrix minus A cubed. And remember, I'm going to write that down without the -1 exponent in this initial step. So without putting the -1 exponent, and I'm going to multiply that by what its inverse is supposed to be according to this problem. So if we just write it out, it would be the identity plus A cubed plus A to the 6th plus A to the 9th. I'm just going to multiply this out. And what am I hoping to get for an answer?
The identity matrix.
The identity matrix. The identity matrix. Guys, we can just FOIL this out. Identity times identity. Okay, that's identity squared plus identity times A cubed plus identity times A to the 6th plus identity times A to the 9th. And then we have to keep going. I'm distributing all these terms out. Then I have minus A cubed times the identity. And then minus A cubed times A cubed. And then minus A cubed times A to the 6th. And then minus A cubed times A to the 9th. I haven't simplified anything yet. Some of you might be thinking you could have skipped a step here or something, and that would be totally okay. But I'm just writing it all out just to be really thorough. We'd get those 8 terms. All right, well, identity times itself is just equal to what? The identity, right? Because it's like 1. So 1 times 1 is just 1. And then here I have Identity times a cubed, well, that's just a cubed. Identity times a to the sixth, that's just a to the sixth. Identity times a to the ninth, that's just a to the ninth. It's just I is like multiplying by 1, okay? And then minus a cubed times the identity, which is just a cubed. A cubed times a cubed is a to the sixth. A cubed times a to the sixth is a to the ninth. And a cubed times a to the ninth is a to the 12th. So you just write all that out. And what do you notice that you can do here?
Dot cancel.
Somebody besides Raphael, what am I going to do on this step right here? You have an idea? Cancel. Yes, I can cancel. So there's a cubed minus an a cubed. There's a to the sixth minus a to the sixth. There's a to the ninth minus a to the ninth. I guess I do need just a little more smidgen of room, but it's not much. The only thing that's not canceling here, guys, is the identity matrix at the beginning and this a to the 12th at the end. But what was given to us in the assumption?
Okay, the 12 equals 0.
Okay. A to the 12th is 0, so it's like I'm subtracting nothing. So guys, look what you end up with. Just the identity. Yeah, which is what you wanted to get. That's what you wanted to get. Make sense? Okay, pretty easy. That's 35. Let's also do 34. 34 is actually even shorter. Let's read it together. 34 says, if A, which is n by n, is invertible and symmetric, then the inverse of A is symmetric. So my first question is, do we remember what symmetric means? Exactly. So that's good memory. A symmetric matrix is one that is equal to its own transpose. So what this is telling us here at the beginning is that since A is symmetric, it is equal to its own transpose. And what I'm trying to show now, I'll start my solution here. What I'm trying to show is that A inverse is symmetric, meaning that when you transpose it, it's just equal to itself. Let's just check it. So I'm going to take A inverse, and the issue is when I transpose it, is it going to be equal to itself? We would like that to be true. What am I going to do as a first step here, you think? See some of you looking in the right place. Right. If I see A inverse transpose, what's my knee-jerk reaction probably going to be at this moment, Oscar?
Would you like to multiply the inverse of A with the just A, right? The A.
I don't need to do, that's way too complicated. So if I just want to simplify what's here, what is it equal to, guys? That's all I'm really saying.
A inverse.
No. Don't. It's just from this equation. We see it right here. A inverse transpose is equal to A transpose inverse. So we just put that in here. A transpose inverse, this is by our theorem. And what can I do with this? So I used my theorem that we just reviewed a few minutes ago, but I'm assuming already that I can replace A transpose with A, because I'm assuming that A is already symmetric. So this is just A inverse. So this step is since A is already symmetric. Guys, that's the whole solution. I've transposed A inverse and shown that it's the same as A inverse. That's what it means for A inverse to be symmetric. So there's really nothing else to do for that problem.
That was like proving that because it was symmetric, or proving that it was symmetric.
I proved that A inverse is symmetric.
Okay.
All right, any questions on that one? Just real short. The longer problems on this homework are just the Gauss-Jordan problems, but I've gotten soft in my old age. I think there's only one or two of them to do in the homework, so it goes pretty fast. Did anybody have any other questions on kind of this section? The homework that's due tonight or anything like that? Pretty smooth. One last little thing I want to do here to kind of wrap up chapter 2, and then we'll take a little break. It turns out there's lots of different ways. Somebody was even asking me about this earlier today. There's lots of different ways to try to decide if a matrix is invertible or not. One is, well, you can try this Gauss-Jordan method and see if it works. But that's a little bit cumbersome. So what mathematicians have done is they've developed a theorem that I'd like to write down for you here. It's called the invertible matrix theorem. And this is actually in section 2.8. This is a very, very short little section. We will actually not have any homework on this. It's just a kind of write it down and reflect on it kind of a moment that I want us to have. And what it says is, and by the way, this theorem is so important that it's actually in the back flap of the book so that you can find it real easily. But it just says, let A be equal to an n by n matrix. And then what it says is the following are equivalent. The following are equivalent, okay? What I'm going to do in this theorem, guys, is I'm going to make a list of statements right now about a matrix, a square matrix A. I'm going to make a list of statements. And the way you're supposed to understand it is everything in that list goes together. Meaning if one of them is true, then everything in the list is true. If one of them is false, then everything in the list is false. They go as a package deal. The first thing in the list, this is item A, is simply that A is invertible. So that is the first item in the list. A is invertible, i.e. there exists A inverse with A times A inverse equal to the identity equal to A inverse times A. I'm just recapping what's already on the board here. Okay, so the first statement in this list is that your matrix is invertible. You with me? What that means is that everything else I'm about to list, I'm going to list about 6 things right now. Everything else in this list would also be true for an invertible matrix, but would not be true if the matrix was not invertible. Okay, and here's item B. Okay, item B is that if we look at a linear system, so let's just write it as AX equals B. This linear system has a unique solution for X. If your matrix is invertible, there will be exactly one solution. Remember our follow-up example from a few minutes ago? There was only one solution to that system because the coefficient matrix was unique. In fact, not only is there a unique solution, we know what it is. The unique solution is just that X would be equal to A inverse times B. So that's no surprise, right? I'm just summarizing things that we already probably know. Let's make another statement that is also part of this package deal, right? So if A is invertible, then this linear system has a unique solution. And now I'm gonna, in part C, I'm gonna make an even easier linear system where I look at A times X equals 0. And I'm just going to say that this has only the what's called trivial solution. The trivial solution, when I talk about trivial solution, I just mean X, the X vector for the solution is just 0. Okay, so if you have basically all I'm saying here, guys, is that if the B is 0, right? If the right-hand side values are all 0, then your unknowns will all be 0. There's only the trivial solution to that system. Okay. Got a couple more things here. Let's go on to part D. What do you suppose for an invertible matrix, and it's an n by n matrix, what do you suppose would be the rank of an invertible matrix? I'm going to remind you, the rank is just the number of pivots. So when you put the matrix into the row echelon form, the question is, how many pivots do you think you would have if the matrix was invertible? So that it kind of goes with this whole thing. Yes, I have an idea.
N?
It's n. Yes, that is exactly right. It is n. What that means basically is that you have pivots in every single row and column of your matrix. They go right down the main diagonal. If you look back at the warm-up problem in your notes there, you're going to see 3 pivots going right down the main diagonal of the matrix on the left. That's another telltale sign of an invertible matrix. It should have full rank. Full rank. In other words, there's no rows of zeros. We made that comment earlier. If we try this Gauss-Jordan method and we get a row of zeros at some point, that's a red flag that it's impossible to get an inverse for that matrix. Okay, so for a matrix that's invertible, we should not have any rows of zeros, which means we would actually have pivots in every row. Yeah, exactly. Okay, so that's a nice one to know. Let's write down a couple more things here. This next one is not so important, but I'll write it down anyway. We would have to look back to last week's notes to really digest this one, but I'll just add it to our list. A can be expressed as a product of those elementary matrices. And we talked about this last week a little bit when we were building up to the Gauss-Jordan method. Elementary matrices, those were just the matrices that occurred after you did one ERO to the identity matrix. Those were what we call elementary matrices. We're not really going to need this item, and we're not really actually going to be talking about elementary matrices anymore. Kind of done with that. Been there and done that. So I won't spend much time explaining this one in more detail, but if you look back at your notes from last week, you could probably make that one work. The last one I want to put here, guys, is that if A is invertible, you should be able to do EROs on it and turn it completely into the identity matrix. Well, that's really just stating what the Gauss-Jordan method does. The Gauss-Jordan method takes your matrix A and does EROs on it so that it becomes the identity matrix. And that's really, this is just a shorthand way of writing that. So this would also be true. So these are 6 things that all live together and die together, right? They go together. If one of them is true about a matrix, they're all true. If one of them is false about a matrix, they're all false, right? So they all go together. They all go together. All right, so this is the invertible matrix theorem so far. Brandon?
Can you explain C again, please?
C is it's the same as B, really. It's really the same as B. The only thing is it's sort of a special case where the B vector in your so imagine you have a linear system and all of the equations on the right hand side, they're all just equal to 0. Okay. What this is saying is that, well, if your matrix was invertible, then the only solution to that kind of system is the 0 solution. Actually, so you could think of it this way. X is A inverse times 0. If I want to use the same notation as I did in part B, the X would be A inverse times 0. Well, if you take a matrix and multiply it by 0, it becomes 0. So yeah, so that's how that comes about. Okay. Any other questions so far? So if I hand you a matrix and I ask you if it's invertible, you've got sort of 5 other alternative ways to convince yourself of it. Yes or no, right? Actually, the theorem doesn't end here. This invertible matrix theorem has parts A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S in this book. We are just starting on this theorem. Now, a lot of the other things I want to add to this list, we have not learned about yet, but we're going to be learning about them. And as we do, I'm going to come back to this theorem and I'm going to add to the list every time. Okay, and by the time we get to the end of the semester, we'll go most of the way through the alphabet of things that are equivalent to having an invertible matrix. Oscar.
And you said if one of them is true, they're all true.
They're all true. And if one of them is false, they're all false. So it's really one of the most important theorems in linear algebra. It really is. It's like a summary of everything in one place. However, I would have to tell you that at this moment in time, I'm not too impressed by the theorem. Why do I say that? Well, if somebody hands me a matrix and asks me if it's invertible or not, am I really going to want to see if I can express it using elementary matrices? That sounds like a lot of work. Am I going to want to try to reduce it all the way to the identity and just fumble through some EROs and see if I can get it to work? That sounds like a lot of work. Am I going to take a linear system and see if I can solve it uniquely? That sounds like a lot of work, right? In fact, almost everything on this list, if I want to figure out the rank of a matrix, I've got to do all these EROs, right? Actually, almost everything in this list, if somebody says, is A invertible, and you want to use your list, you're pretty much going to have to do EROs. Either with the system, this linear system, or to count how many pivots you have, or to try to row reduce it to the identity. These are ERO heavy observations. They really are. It would be so nice, wouldn't it? It would be so nice if there was something in this list that was free of EROs. No EROs, something easy, something we could just glance, at least do a little less work than a whole series of EROs. If there was something in this list that was just like, ooh, that's an easy one to remember, and I can just test it real quickly. So I'm going to add one more thing to the list right now. All right, and then I'm going to make you wait 10 minutes to find out more about it, like I always do. But there's one more thing that I'm going to put in the list that we have not learned yet that we're about to learn, and it is called the determinant of this matrix. And I'm going to write it as DET of A. And as I'll explain after we take a 10-minute break, the determinant of a matrix is just a number. It's just a number. There's no EROs, there's no vectors, there's no system of equations. It's just a number. And as long as that number is not 0, that's going to be another telltale sign that our matrix is invertible. So if somebody gives us a matrix and says, is it invertible or not? This is maybe, just maybe, going to be the one that we really, really want to use. Actually, I have a funny story about this determinant thing. So I'm an algebraist. I was doing my PhD at Berkeley. and I had my professor who was an algebraist, and he wrote a book and had a very interesting chapter in his book. His book was about non-commutative algebra. But he was friends with a professor at San Francisco State. So Berkeley's on the Bay Area, the east side of the Bay. San Francisco State, right across the Bay, there's this math professor over there. He's fairly famous. His name is Stephen Axler. And Stephen Axler was a friend of my PhD advisor. And he was also an algebraist. And he also wrote a book. And the name of the book that Dr. Axler wrote was Linear Algebra Done Right. That's what he called it. It's a famous book. You can find it online very easily. It's called Linear Algebra Done Right. So I had to get a copy of this book because it was my PhD advisor's friend. And I looked in the book, and the first thing I noticed is he has a chapter in his book that's called Down with Determinants. Down with Determinants. I wonder, well, what's that about? Apparently, this guy does not like determinants. And he does this whole book he does all of this linear algebra stuff, systems of equations and linear independence and vector spaces and all the stuff we're going to do later in the semester. He does it all without ever using determinants. And then he has some appendix chapter at the back of the book about determinants, just in case somebody wants to know something about them. But anyway, so he wrote this book called Linear Algebra Done Right, where he didn't use determinants at all. Well, turns out my PhD advisor loves determinants. And I was looking through his book because he wrote a book also on linear algebra. And I just happened to notice that in my advisor's book, there's a chapter called Up with Determinants. And so these guys are like having this little tussle back and forth across the bay with their two books. And my advisor really, really likes determinants. Well, I, of course, had to decide with my own advisor. I did want to graduate. So, so I decided to be in the Up with Determinants camp. And I'm going to really try hard in the second half of our class today to explain to you why I think determinants are so awesome. The fact that it's in this list is the first reason. The fact that we can use determinants to decide if a matrix is invertible is going to be a really good reason, in my opinion, that we should care about determinants. So anyway, I'll save that drama for after we take a short break. Let's take a 10-minute break right now, guys. I'll let you get some fresh air and whatnot. When we come back from the break, I'm also going to talk about our midterm that's coming up. Okay, so I'll see you guys in about 10 minutes. Please.
So if one is true, then the rest is true.
That's right.
So if one is false, then the rest is false.
Right.
So how do I know? So if I know, so this one is true,
Uh-huh.
then this one is false.
Well, that's not if this one is true, then this one must be true. This one must be true. This one must be true. They would all have to be true. Yeah, that's what the theorem is saying. Yeah. Yeah. Good question. anything?
We're finding all of that.
Anybody do anything fun over the weekend?
This is Super Bowl.
The Super Bowl. I did not watch the Super Bowl. I went hiking. Did I tell you that? I think in my email I said that. Yeah. Oh my God, I was so scared because the mountain I was climbing is called Rattlesnake Peak, and not only that, I ended up off the trail. Like
Oh.
I was trying to be clever. I went up one way on a trail. I thought, oh, I could go down the other side. And I saw a little faint path. So I thought, oh, I'll just follow that. Well, the path petered out halfway down. Now I'm like walking on top of like stuff I can't see very well below my feet. And I was like, oh my God. But luckily it's February. I think the snakes are still sleeping. So I made it back in one piece without any problem. But I was all by myself and I was like, this is probably not a very smart idea. It was actually a pretty hard hike. But the nice thing was after I was done with the hike, I drove straight home with no traffic because the Super Bowl was already going on. It seemed like nobody was out on the road. I'm like, it should be like this all the time. That'd be really nice. Anyway. Good times, good times. Yeah, I really do enjoy hiking. I think I'm gonna go ahead and get started here again, guys. Before we go any further with the math, I just want to pull up our Canvas page and talk a little bit about our midterm. So if you go to the home screen of our Canvas page, there is a section, of course, called Files. So I'm going to hover over here on Files. And one of the folders that is in here is something called Midterm 1 Resources. So I'm going to go ahead and click that open so I can show you some stuff. Now, in this folder, there is a lot of stuff. The first thing to understand about this folder is that it is 100% optional. Nothing here is being assigned or collected. You don't have to do anything that's in here. What is in this folder? Well, First of all, there is a review, I'm gonna kind of go out of order here a little bit. There is a review session which has about 10 problems on it. And in that review session, you can also read the solutions to those review session problems. But the main thing is that I actually have a video of the review session. So let me actually show you where that is. Canvas won't let me put videos inside of this files section. If you hover over the pages section though, that's where all the videos are. That's where these additional videos for the class are at. Also my class lectures. Some of you might have noticed that I've been putting our class lectures that I'm recording into that folder. But there's also a folder here that says midterm 1 review session. So if you want, you can click onto that. And what you're going to see in here is about, well, I chopped it up into 3 30-minute videos essentially. So altogether, it's about an hour and a half of me doing the problems that are in that review session document. If you don't want to watch an hour and a half of me talking about them, you can just do the problems yourself. Or you can just not do it at all because you don't have time or you don't want to do it. But this is optional. If you're looking for something to study, you could watch that video. And that is, as I said, associated with, let's go back to the midterm 1 resources folder. That is associated with this review session here at the bottom. The other compromise is you could say, well, I don't want to watch the 90-minute video, but I at least want to just read the solutions and kind of check them with my own work. So that's one thing that you can do.
Is that in the solutions one? Does it have like the work shown for it?
Yeah, all the work shown. All the work is shown. The other document right here is midterm 1 review. I'm going to open this one up. This one is just kind of all the information that you need. So like I put TBA on when the exam is, but I can tell you now when it's going to be. It's going to be next week on Thursday, so February 19th. And then I have just kind of a, let me just scroll down a little bit here, what it's going to cover. So chapters 1, 2, and 3. By the way, we're going to start chapter 3 in just a few minutes. And then this is just like a vocabulary list of the important words in these first 3 chapters. So you can use it kind of like a checklist. Just make sure you know what all these things mean. And then I have a things to be able to do list. So you can kind of go through it. Okay, I should be able to do the chemical mixing problems. I should be able to solve Bernoulli differential equations. I should be able to convert a matrix to row echelon form by doing EROs. Right? There's a whole bunch of just kind of tasks that you should be able to do. And so you can take a look through this. It's kind of long. Properties of invertible matrices and the invertible matrix theorem, the stuff we were just covering, that's listed there as well. Some of the stuff here at the end of the list is going to be from chapter 3. You haven't quite gotten to it yet. But anyway, so that's something you can look at. And then I have some just general advice about studying, which I'm going to let you read. And then some extra practice problems here as well. Again, none of this is required, really isn't. If you don't have time to do all of these extra problems, you don't have to. If you choose to do some of them though, I have the solutions to them. So if we X out of there for a second, the midterm 1 review solutions document has the solutions to all of those problems in the packet. But the thing that I would really recommend for this midterm next Thursday, that everybody try to do this, is to at least try a sample midterm. I actually have 2 of them here. So there's the lowercase one and the uppercase one. So the uppercase one, first midterm sample, and then the first midterm sample solutions, right? And then there's a lowercase one, first midterm sample number 2, and first midterm sample number 2 solutions. What I would recommend is that everybody try at least 1 sample exam. If you don't do anything else, just so you have an idea like what it's going to be formatted and kind of how long it's going to be, kind of what kind of questions, that kind of thing. All right. And if that's all the time you have is to just do 1 sample midterm, I would at least do that. If you try 1 sample midterm and you're like, no, don't think I did very well on this, or I have some issues with this, then I would go over the solutions and then try to study up wherever your weak areas might have been, if there were any. And then if you had the time after that, I would try the other sample midterm. Okay. So I would probably do that. Or maybe you try the first sample midterm and you're like, oh my gosh, I really am not ready for this. I better go watch the review session, right? And then you could do that before you try the other sample midterm. It just kind of depends on A, how much time you have to devote to this, and B, how well you're doing with the material already. If you're already acing everything and you're totally solid, you don't need to do all this stuff, right? And if you don't have time to do it because you've got just work and family and other classes and stuff, then just do the best you can with what time you do have and try to do as much as you are able to do. I won't really be reviewing in class during our regular class time. So I'm going to be asking you to load up this folder from Canvas and try your best to study as much of it as you feel like you need to study. Okay. So that's that. When we take the exam next Thursday, it will be a closed calculator exam. So no calculators. It will be closed notes, closed book. I will give you a table of integrals, and I will give you the. I think I'll give you the formula for the mixing differential equation because there's just so many parameters in that. I don't think it's worth memorizing that one. But you should really try to learn all of the. So if you're doing a problem and you say, "Oh, I know this is a Bernoulli differential equation," write that down. Oh, this is Bernoulli, and then with n equal to 3 or whatever it is. And then I will be giving partial credit. Somebody asked earlier about partial credit. I will give partial credit for each and every little thing you write down, even if you don't even then solve the problem. But if you told me that it was Bernoulli and you told me what n was equal to, and maybe you even wrote down one of the formulas because you remembered it. If you write it down and you have it correct, I'll give you points for that, right? So try to do your best to learn those formulas so you can at least write them down for credit. It's not a black and white grading, guys. I don't just look at your final answer and say, oh, that was wrong, so I guess I'm going to give a 0. No. If you've basically done the problem right, and maybe you just make a minor sign error and it throws everything off somehow. Like with these EROs we've been doing, that's very, very common. But I really trace through your work carefully and I check, okay, so other than the sign error, do they know what they're doing and did they understand the concept? And if you did, I probably would give you like 90% of the credit on that problem. And if there was a part B that followed it up and you used your incorrect answer on part A, but you then based part B on that and did it correctly as a conclusion from your wrong answer, I'll give you full points on the next part. Even though it's technically not the right answer, I will give you full points for that because you clearly know what you're doing in part B, but you were just using the wrong answer from part A. I try not to make my problems like connect like that too much because that's annoying, but just know that, guys, you don't have to give up on the whole problem just because you're struggling with one little piece of it, right? So tell me everything you know about every problem I ask you, and I will be guaranteeing you're going to end up with a better score, right? So that's for sure. Okay, question, Brandon.
You're gonna get the whole class day?
Yeah, you'll have the whole 2 hours that day. We won't do anything else. What's probably going to happen is you're going to have so we have a homework assignment due tonight. So I'll just give you a preview of the next 2 weeks. We have a homework assignment due tonight, which is probably almost done. The homework for Friday, which is really quick. There will be an assignment for Tuesday that's going to be on chapter 3. But then there won't be any homework for the rest of the week after that. You'll have Thursday for the exam, and then probably what I will be doing is giving you an extra credit video assignment the weekend after the midterm. So, and that will give you points towards your midterm. So that's kind of how the next 2 weeks are going to shake out.
So for sure, no cheat sheet, right?
That's right. That's right. I've never done that. If the problem with the cheat sheet thing is then people spend all their time on the cheat sheet, and that's the whole extent of what they do. And without really learning the material very well. And then it's all just hit or miss, whether it's on your cheat sheet or not. And then I don't know how to deal with partial credit in that case. It's like, oh, well, you know, they wrote it down on their cheat sheet and then they wrote it down on the test. Well, what's that really worth? So I don't tend to subscribe to that philosophy.
All right.
Okay, any other questions? Caesar.
So that Tuesday before the midterm itself, everything in that class will for sure be on that.
Yeah, we will probably be doing some review in the form of group work, and there might be some loose ends we're tying up. We'll answer questions on that homework assignment. So the things we'll be doing on that Tuesday, there won't be a massive amount of new material, but it will be kind of like tying up loose ends. Okay, we got to get this homework done. Oh, here's a group work we can do. And if there was anything I didn't quite cover, I'll have a chance to do that. So I don't think it'll be a super heavy, stressful class. It'll definitely be a good class to come to get ready for the exam.
And just one quick follow-up question on the things to know how to do.
Yeah,
That pretty much tells you pretty much everything you should know.
everything.
Yeah.
If it's not on that things to be able to do list, you don't have to worry about it. Right. Oh, I remember one other thing I wanted to tell you. Do you remember at the beginning of the semester when you were watching videos for this class before we met in person? Before we knew how to solve any differential equations at all, I started off and you watched a video and even did 2 or 3 homework problems on position, velocity, and acceleration. So I think it is in that list, that the things to be able to do list, but I am not going to put this on the exam. I'm not going to do it. So I need to take that off of that sheet. Really, the only reason I have that in this class at all was just because like I wanted to be able to like talk about the basic material before we knew how to solve anything. It's kind of a pain in the rear to deal with these problems, and it's more of a calculus problem than a Math 250B problem. So you can just ignore that one as well. So anyway, hopefully that clears that up. Did you have a question as well?
Yeah, the mock exams are like similar in length to.
Yeah, those sample exams are actually exams I've given before. So and I've been teaching this in the same format forever. So like 2 hours, covering chapters 1 through 3, nothing has changed as far as. And if you look at the sample test, you'll see I never put one of these on there. So yeah, that's why I'm saying I would really recommend the sample midterms as a really good thing to do. At least one of them. If you do one of them and you nail it and you ace it and feel ready to go, that's fine. But it might also tip you off some things you might want to review so that you can then have time to review and then try the other one. So it's just kind of take it or leave it. All of that stuff is totally optional. Yeah. Anything else? Caesar.
Is there any big that you would say like don't do that or no's that you kind of like avoid doing this or when I know some teachers do have stuff.
Avoid, no, I don't think I can think of anything off the top of my head. Try not to make algebra mistakes. I mean, that would be like some very generic thing I could say, but a lot of times people, they can study really hard, they can know the material really well, and sometimes they'll make mistakes on the midterm. I feel so bad. It's like they could have studied for 500 hours and they still make that same mistake. Like it could just be a sign error or just an algebraic mistake with, I don't know, fractions or radicals or something. But it's not really the kind of stuff you're studying that you're going to be studying for. So yeah, I don't have anything off the top. If I think of anything, I'll let you know.
Do you think it's gonna be more linear or differential heavy?
That I do talk about in my review session. So there's going to be 3 chapters here on this midterm. So this is you'll find this in the review folder. I would estimate chapter 1 to be about 40%. These 2 chapters, they kind of go together. So I would say a little over half on chapters 2 and 3. Yeah, that's a good question. Yeah. Okay. All right, well, I will leave it at that for now. We obviously have a couple more classes and we have time to talk more about this, but some people like to start early. And I just wanted to get that on your radar a little bit ahead of time, especially because this week's homework is relatively light. It might be a chance for you to start looking early into some of that stuff in the review materials. Okay, well, also one other thing, I passed out this group work number 4. I've already kind of decided I'm going to wait until Thursday to do it. So if you could just kind of keep it with you and then bring it back on Thursday, I'll have extra copies in case you forget. But we won't do that one today because I am just too excited to be up with determinants. And I want to tell you about that. So let's do it. This is chapter 3. The shortest chapter in the book, guys. It is not very long. And so we will be able to finish this chapter entirely before our exam next Thursday. So determinants. Now, in order to talk about determinants, the matrix that you are working with has to be square size. So it doesn't make sense to talk about the determinant of a matrix that's not a square matrix. So it has to be n by n. And the idea here, the idea behind this, and then I'll get into the details in a minute, but the idea is to associate with the matrix A, just n by n, a number. And that number is written DET of A. Or there is another notation besides DET of A that you will sometimes see. I don't like it very well, but I've noticed some other professors do use it, which is you can put these bars around the capital A. It almost makes it look like absolute value bars, but that's not really what it means. It's just another notation. So in case you won't see me use this notation, but you might have another professor somewhere along the line who likes to put bars around determinants. That's really the only reason I wanted to mention it. And then the main theorem that I've already kind of mentioned, guys, is that your n by n matrix A is invertible if and only if the determinant of that matrix is not 0. So this theorem, for the moment, I'm basically just telling you that theorem, but it fits in with our list here, right? So the following are equivalent. A is invertible, and then all of these things are either true about A or false about A, and the determinant being not 0 is in the list, okay? So now I have to tell you, how do you find the determinant of A? How do you find this number that goes with the matrix? Excuse me. So what is the determinant of A? Well, let's just start off with a very small matrix. Suppose that we have a matrix that is only 1 by 1. It is a 1 by 1 matrix, little a. You won't be surprised, guys, that the determinant of a single 1 by 1 matrix is just whatever that number is that is in that matrix. So very, very unexciting, the determinant of a 1 by 1 matrix. Let's go to a 2 by 2 matrix where things get a little more interesting. So let's suppose that we have the matrix A and B on the first row and C and D on the second row. How do we take the determinant of this matrix? Well, the formula is going to look familiar to you. It is actually A times D minus B times C. And that little expression has shown up already. You might remember. So AD, that's the main diagonal values. And then the B and the C are the off diagonal values. And you might remember that for a 2 by 2 matrix, it was going to have an inverse only when the AD minus BC is not 0. So it's totally consistent with what's in the box. Totally matches up with what's in the box. AD minus BC is not 0. Okay, so that's the definition of the determinant for a 2 by 2. Let's go to a 3 by 3 matrix, guys. Let's take the determinant of, let's say it's ABC, and then DEF, and then the bottom row is GHI. Okay. And leave a little bit of space off on the right, if you would, because I'm going to put something there in a minute. But below here, I'm going to write down the formula. Okay. What is the determinant of this matrix? Well, the formula is AEI plus BFG plus CDH. And then minus CEG. And then minus AFH. And then minus BDI. Well, that is a alphabet soup of letters that the first time somebody showed that to me, they were like, and you must be kidding, you expect me to memorize that? Because the letters are kind of all over the place. It's kind of a big jumbled mess. Turns out, guys, there's actually an easy way to remember the formula. I never remember this. Instead, what I do is I use this little visual trick. I take the matrix and I recopy. Let me use I'll just recopy the first two columns. So just off to the right here, this is why I wanted you to leave a little bit of space. I'm just going to recopy those first two columns just to the right of the original matrix. And again, this is just a device for remembering the formula. Okay? And then what I'm going to do, guys, is I'm going to start drawing some arrows into this diagram. So if you make the main diagonal arrow here, AEI, that's exactly the first term, right? That's the first term. And then if I just slide to the right, if I just sort of translate over to the right, the next diagonal to the right is BFG. And if I do that one more time, the next diagonal to the right is CDH, just like that. Okay? Now, once I'm done with that, I'm going to start drawing diagonals. I'm going to start drawing arrows differently. I'm going to go from the lower left to the upper right this time, and I'm going to look at the letters there, CEG. And that has a minus on it. And then if I again slide to the right, AFH has a minus on it. And I'm going to shift this diagonal again to the right. Translate it over, I get the BDI. Notice that all of the red arrows come with sign changes. So the last three terms have a subtraction on them. So you're going to need to do sign changes. Whereas the first three arrows, which I drew in blue, do not have sign changes. You just literally write down whatever you came up with. So the name I like to call this the arrow method. It's the arrow method for finding this determinant. So it's the arrow method for a 3x3 matrix. It's the arrow method for a 3x3 matrix. Okay. Now, I won't do an example yet because so far all it is just plugging numbers into this formula. It's a very easy thing. But what I can tell you is that already with what is on this much of this board, you can almost completely do Friday's homework. It's really, really quite short. So that's just a quick overview of matrices up to 3x3 sizes. Now, the next question is going to be, what if n is greater than or equal to 4? If my matrix is even larger, how do we find the determinant in this case? Well, again, as soon as the matrix gets this big, I can't really just give you a quick formula and just spell it out on paper, right? Instead, for these larger matrices, I'm going to be giving you sort of a procedure for coming up with this. But keep in mind, guys, at every single level, the determinant is just a number. It is just a number, and whether that number is 0 or not tells me whether the matrix has an inverse. So before you go launching into the Gauss-Jordan method, for example, let's say I give you a matrix and I'd like to find A inverse if possible. Might not be a bad idea to take the determinant of that matrix first to just see, is it going to even be invertible? Because if it's not, let's save ourselves a little bit of time, right? Let's save a little bit of effort. But what about these larger matrices? Well, we need some definitions here and a little bit more of a of a buildup for this, okay? So I need a definition, and I'm gonna start with this one here, guys. If, sorry, I didn't mean if, the I comma J minor, I'm gonna underline that because that's the word I'm gonna be talking about right now. And the notation for the minor, the IJ minor is just going to be M sub IJ of capital A is the determinant of the n minus 1 by n minus 1 submatrix obtained. So we're going to take an n minus 1 by n minus 1 submatrix obtained by deleting row I and column J. That's the way we're going to do it. It is the determinant of the n minus 1 by n minus 1 submatrix. So your original matrix is n by n, and now you're going to remove one row and one column. So the size of this submatrix is n minus 1 by n minus 1. Let's just immediately go into an example here. So as an example, EX stands for example. I'm going to give you a matrix that is 4 by 4. So let's take this one. The first row is just 1, 2, 3, and 4. And then on the second row, I have -1, 1, 5, and -2. And then the third row is going to be 0 and 3 and 0 and -1. And then the fourth row is 2, -2, 1, and -3. Okay, so let's take that. And now you have to understand there are 16 different minors in this matrix, right? There's 16 entries here in this 4 by 4 matrix. And so there's 16 different IJ combinations, right? So I'm not going to do 16 examples right now. Let's just find one of them. Let's find M of 3, 4. Just to practice. Okay, so let's just see if we can find one of these minors, just to get the hang of this. So for the solution, how does this work again? To find M3, 4, it's going to be the determinant of the submatrix that we get by crossing off row 3 and column 4. So I'm going to kind of draw a line through this. Now you got to be careful especially if you're still doing notes on paper or pen. If you keep crossing off lines and so on in your matrix, you can kind of lose track of what the numbers were saying. So just be a little careful with that. But you're just going to take the determinant of the matrix that's left. So it's going to be a 3 by 3 submatrix in this case. And I'm just writing down the numbers that did not get crossed off. The numbers that did not get crossed off. Okay. And because this is only a 3 by 3 matrix, I actually do have my arrow method that I can use to find the determinant of this one. I'm going to recopy the first 2 columns off to the right of this matrix, just like we were commenting over there. And I'm going to start drawing my arrows here. The first diagonal is 1 times 1 times 1, which is 1. The next diagonal is 2 times 5 times 2, which is 20. Plus the next diagonal is 3 times -1 times -2, which is 6. Okay, and now I'm going to draw I guess I was drawing them in red earlier. I'm going to draw my diagonals going the other way. So minus 2 times 1 times 3 is 6. And then minus -2 times 5 times 1. So that's actually minus -10. And then minus The third arrow is 1 times -1 times 2. Well, that's -2. So we have minus -2. So you do have to be careful with your signs on this because there can sometimes be double negatives that you have to be careful with. In this case, we're just gonna add all of this up and we're gonna get 1 plus 20 plus 10 plus 2. And if you add all of those numbers up, guys, the answer that you should come up with here is 33. So the 3/4 minor is equal to 33. Again, there's technically 16 different minors. And if you're out there wondering, well, am I gonna have to find all 16 minors to do the determinant of a larger matrix? The answer is actually no. You will not have to work that hard. Okay, so we're gonna get to the punchline here in a moment. Let me make one more definition. Are there any questions though? Sorry, don't want to go too fast. Isaac.
So how do you explain one more time, how do you know that the I and J you're eliminating won't collapse the system to 0? Like, is there a way?
I mean, if I'm only removing one row and one column from something that was n by n to begin with, then what I'm left with will always be n minus 1 by n minus 1. You can't collapse it any more than that. Yeah, for sure. Kim?
But for the n minor, you can either be 4 by 4 or.
Any size, it could be 5 by 5, it could be 7 by 7. Actually, this still works even for the smaller matrices. So even our little 2 by 2 matrix here, guys, has minors. There's M11, M12, M21, and M22. Yeah, so the size of the matrix really could be anything. Yeah. That answer your question? Okay, great. Everybody else okay so far? Okay, now we have to talk about just a very related definition, which is the cofactors. So the definition here, guys, is the I, J cofactor. And this is written C sub ij of capital A is, well, this one I can give you just as a formula. Cij as a formula, guys, is the following thing. It is basically going to be the same as Mij. So we already learned how to find the minor Mij here. This cofactor is going to be the same thing as that minor, except that sometimes, approximately half of the time, we have to do a sign change. Namely, -1 to the power of I plus j times Mij. Let's put that in a box here, guys, so we can clearly learn that formula. This is the kind of thing you will need to know next Thursday. How do you find the cofactors of a matrix? So what you're doing here, guys, is you are calculating the minor first. And then depending on I and j, if they add up to an even amount. So guys, think about what happens when you take powers of -1, right? Powers of -1 are either going to be -1 or +1. And they're going to kind of go back and forth depending on whether I and j are positive and negative. And in fact, I like to draw this little rubric here, this little visual to help me remember, where do I have to make sign changes in calculating this cofactor? And the answer is anywhere that there's a negative on my little diagram here, that would be a place where the I, J values add up to an odd number. Yeah, so let me just get my camera on that. So the I and the J values would add up to an odd number in the places where, like, so for example, this position here is I equals 1, J equals 2. Well, 1 plus 2 is 3, -1 cubed is -1. So I would have a sign change on that one. But the ones that are where I plus j is even, -1 to an even power does nothing. It's just, then in that case, the cofactor and the minor are the same. What I'm trying to say is the minors and cofactors are almost the same thing. The only difference is that sometimes there's a sign change. And the sometimes is dictated kind of by this diagram. This is worth writing down, by the way. This diagram is a good way to remember how the sign changes work in this matrix. So as an example, as a quick example here from above, let's go back to the example we were just doing a moment ago. From above, what would be the 3,4 cofactor of the example that we just did a minute ago? So we look at the 3,4 minor. The 3,4 minor was 33. And all we have to ask ourselves right now is, do we need to make a sign change? Yes. And we do. The 3,4 position, guys, is right here. I see a minus sign on it. The other way to think about it is, well, 3 + 4 is 7, which is odd. Odd powers of -1 are going to result in minus signs, right? So this would be the negative of 33 in that case. It's going to be the negative of 33. Okay? And the last thing I want to do before we are kind of out of time is I'm just going to write down how you get the determinant of any size matrix once you understand how cofactors and minors work. And admittedly, I need to come back to this on Thursday and like doing a full-blown example, but I just want to get the theorem down first. Is that a hand, Oscar?
Yeah,
Please.
I was gonna ask, could I be lazy and do the determinant and then just multiply by -1 to get the cofactor, or was that not possible at all?
No, that's fine. I think you're saying the right thing. So you just find the determinant of this,
Yeah.
which we did, right? That's actually most of the work. So you're not being lazy. You're doing most of the work to find this whole determinant. And then the only thing is, oh, I'm working with the 3,4 position, so the cofactor has to have a minus sign on it. That's all. Yeah, so just change the sign on that. Okay, so let's write down, we'll wrap up today's class with this. This is the cofactor expansion theorem. You're not going to need this, guys. You're not going to need this cofactor expansion theorem for Friday's homework. So you can go, by now you almost could already do Friday's homework, just based on this little bit that we've talked about. It's a quick assignment. So, but this is for larger matrices. So let A be an n by n matrix. I'm going to write down the theorem and then we will practice it on Thursday at the start of class. Basically what it says is it gives us a formula for the determinant of A. It is going to be a formula. Actually, it's going to be not just one formula, it's going to be an entire collection of formulas, any of which is correct. Okay? So let me write it down. Give yourself sort of 2 lines here to write 2 formulas. The first one is going to look like this. It's a little messy when I first write it down, but I promise it's not really anything too bad. So little ai1, ci1. By the way, these c's are just the cofactors. They're just the cofactors, right? So ai1, ci1 plus ai2, ci2, and plus ... up to ain, cin. So it's just those terms. And when I do this formula, this is kind of considered expansion on row I. So I would call that expansion on row I. Now let me just explain. Again, I don't have time to actually do an example right now, but just so you understand and don't get too scared of this formula. All it is saying is pick whatever row you want. It doesn't matter. And with that row, you're going to go across that row and you're going to take the entries from the matrix in that row and multiply them by the corresponding cofactors. So if I pick row 1, Then I'm just gonna do A11, C11 plus A12, C12, and so on and so on and so on. We're gonna talk on Thursday about whether, like, even for this matrix, maybe there's a good choice of a row to choose. Think about that. But actually, turns out you don't have to pick a row. You can choose a column instead. So I'm gonna write a second formula down. A1J, C1J plus A2J, C2J, and plus da 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 da, plus ANJ, CNJ. And this would be considered expansion on column J.
Why do you have the one and the J reverse instead of like they had on top of
It's
it?
because you're switching from rows to columns here. So the subscripts, the first subscript is the row number and the second subscript is the column number. So guys, with this matrix on Thursday, I'm gonna find the determinant of this matrix. What that theorem tells you is that you have 8 different choices. You can expand row 1, expand row 2, expand row 3, expand row 4, or expand column 1, expand column 2, expand column 3, expand column 4. It might not be obvious, but any row or column is going to give you the same answer. Right? And actually, last thing, does anybody think they have an idea what would be the best choice of a row or a column to expand on in this matrix? Arnav?
Row 3.
Row 3, you see that A31 is 0 and A33 is 0. So that would mean that over here, a couple of your A values are 0, and you don't have to calculate as many cofactors. That was a little quick. We'll come back on Thursday. I'll say all of that again, and we'll actually finish an example. Guys, thanks for hanging with me today. And I will see you all in my office hours or in class next time.